All right, so we stopped at 20, so we're picking up at 26. So these say, give a formula for the extended function that is continuous at the indicated point. So f of x is equal to x cubed minus 1 over x squared minus 1. And it says that x is equal to 1. So if I just plugged in 1, what's going to happen?
0 over 0.
Yep, 0 over 0, which is a problem. So I need to see if I can factor this to reduce it down to be able to plug 1 in, basically, is what I'm trying to do, which is going to make it continuous. Because right now, there's a problem. So how would I factor well, let's factor the bottom first because it's easier. So how would I factor the bottom? What is this?
X minus 1, x plus 1.
Yep, x minus 1, x plus 1. And then the top is a what?
It's a triple. It's a
Difference of cubes. And so what does that factor into?
x. And then is it x minus 1, x plus 1?
There's like a third
And then,
This is soap.
right.
Oh,
So x squared
same.
Yep, so that was same.
minus 1 or plus 1.
Opposite?
Opposite, so plus.
There's 2 ways.
Yeah. Wait, close.
Nope. X.
So wait, what's so weird?
The middle term is this term times this term.
Okay.
And then, what's the last one? What's the AP?
Plus 1. Wait, plus 2.
Always positive, so plus. And it'll be 1. Technically, it's 1 squared. Okay. But obviously, we don't need to write that. So soap, just as a refresher, is same sign, opposite sign, always positive. Oh my gosh. I cannot write going down, apparently. Good enough. So now what happens?
The
X
x minus 1 cancels.
Yep, x minus 1's cancel. So I end up with f of x equals x squared plus x plus 1 over x plus 1. So now if I plug in 1, I'm okay, right?
Yep.
Yep. So now this would be continuous at x equals 1 by doing that, is what we were trying to do. Okay, because the instruction said, give a formula for the extended function that is continuous at the indicated point. So basically, we simplified it down so that now we are continuous because before we would have had an asymptote at 1. Along with other issues since it was 0 over 0, because that's its own set of issues, but anyways. Alright, this might not be the best example, but we're going to do it anyways. F of x is equal to what?
So that makes me nervous.
The sine of 4x over x. And x is equal to 0. All right, so this one is a little bit weird because in and of itself, you probably wouldn't know what to do with it. So this is gonna, to an extent, take a little bit of you just trusting me in how we write this, but I want you to have seen it because it is a little weird. So with this one, there's nothing we can immediately see that we can like factor out, right?
Yeah.
So I essentially need to write like a conditional function in a sense where if x is not equal to 0, it's this. If x is equal to 0, it's this. So it's going to be f of x is equal to, let me have the little curly Q thing. I know it has a fancy name of some sort, but I like calling it a curly Q, mainly because I never remember what it's supposed to be. All right, so when we have sine of 4x over x cannot be 0, okay, because that causes a 0 in the bottom, and a sine of 0 is 0, so there's other issues there. So this is going to be the function when x is not equal to 0. Then we take this number that's in here, okay, and when x is 0, that's just the value. So it's 4 when x is equal to 0. Because that would be the only time when that could be the case, basically. And so anytime you have one like that, like the sine of something x over x, it's going to be this way.
Okay.
So I would say just like more or less memorize that fact, that that's the case.
Oh, that's the answer.
Yeah, that's our new function. We basically just had to split it because we couldn't have 0. So we just had to write what it would be if x was 0 to be allowed to do that. All right, the next problems deal with Theorem 7, so I'm going to scroll back up and look at Theorem 7 just for a second so we see what we're dealing with. So composite of continuous functions. If f is continuous at c, then g is continuous at f of c, and g is continuous at f of c, then the composite function g of f is continuous at c. So these say to show that the given function is continuous. So they give us 34 f of x is equal to the sine of x squared plus 1. And so basically, if y'all remember, I want to say it might have been in pre-calc, might even be all the way back to algebra 2. We were given this and we basically said what two functions make up this composite function. And so we were breaking it down. That's essentially what we're doing here. Okay, so we're coming up with two functions that when you smush them together, give me this.
Okay.
So I'm just going to call them g of x and h of x because the whole thing is giving me f of x. So g of x is equal to and h of x is equal to. So h of x is going to be like my what's getting plugged into the other function. So what would we say h of x is then?
X squared plus 1.
Yep, x squared plus 1. And so then g of x would be
Sine
sine x. So then we can say g of h is continuous by Theorem 7. Okay, now you don't have to write that every time, but that's what we were trying to find here, so that's all we're doing. I'm guessing we're going to get intermediate value theorem later because I don't even see a problem that goes with that. So I guess I just wanted you to be aware of it at the time and then go from there. Alright, well, I'm gonna go ahead and give you problems. Tomorrow will be in the next section, which is rates of change and tangent lines, which tangent lines will become a very good friend of yours this year.
A good friend.
A helpful friend.
Necessary friend.
It's kind of like the unit circle.
Mm.
Maybe not quite as much of a bestie, but
Yeah,
it's
definitely.
gonna be
Unit
there.
circle is actually
All right, 1, 3. Um, 11, 13, 15, 21, 23, 25, and 35.